Oh yeah, we've all been there.
Yeah.
All right. Online Jack. Hi Jack. Can you hear us? If you can hear us, please either thumbs up or a message, or you can speak. I just need to know.
I can't hear it.
If you're speaking, I can't hear you. Yes, thumbs up.
Okay.
Cool. Okay,
Sick.
that's great. Yeah, live stream is up, and I do not like my face in front of the camera. Anyways, this is for Lucy.
Awesome.
We've got the slides, so we will do. I can remove this slide, or we can add yours. But we have to read out a disclaimer.
Yeah.
I'll do an acknowledgement of country at the start as well. Acknowledgement country. Do a disclaimer and then introduce Lucy. And then she'll take it over and do her magic.
Yep. Sounds good.
And then my sister's having a biscuit with a coffee.
Nice.
Off topic. Now this is officially on live stream. Oh, and I have to remember to
Because I think last year when I took this class, or last time when I took this class, they actually posted a link to this, like the YouTube thing. But it was from like 2017 or something like that.
Yeah, probably.
But yeah.
But yeah, no, this year we had trouble. I sent the lecturers the wrong date.
Oh no.
Because one of my officers sent it.
Yeah.
And we were sending emails back and forth. And then I needed to change the description because the lecturers asked that we do. And once I did, I just copied whatever my officer sent and I pasted it without confirming with the information.
Yeah.
And it turns out my officer had the wrong date on it.
Oh no.
So if not that many people show up, I wouldn't be surprised because we had the wrong date. We did fix it on Instagram, and I did message the lecturers again, but we'll see how it is. Hello. But yeah, I'm gonna move off of I can't even speak. Offering arms to connect.
I tried to convince the rest of the insects to come, but we'll see.
I tried to.
And most of my team was in like the middle of them. Yes. Nice to meet you.
Lovely. We just need to share screen. Do you want to do it on your laptop?
No, honestly, don't need to, not necessarily.
Okay, good. So one of the things that I just need to start the recording. You're live on YouTube, by the way.
I've never been live on YouTube in my entire life.
But it's a little bit delayed because of the
Evidently. That's trippy.
But yeah, you don't have to look at it. I'll do acknowledgement of country. And then I'll read out a disclaimer. We'll skip this slide. And then I'll introduce you. It's like over. Then it's up for 2 hours.
Can do.
Yeah. I'll be sitting there monitoring a Zoom.
Bye-bye.
But yeah. But yeah, and we just need to start the recording. Oh, it's 10 o'clock. Maybe wait 5 minutes because I forgot who else to walk in.
Most should start 5 past the hour anyways.
Yeah.
That makes sense.
Does that sound good?
Yeah, 100%. Thank for it.
Alright, cool.
Are the slides from Sem 1 this year or Sem 2 last year? Doesn't matter.
I think it's this year. Yeah, but the SQ ran along on this someone. I'm pretty sure.
I'm pretty sure it was someone.
Yeah.
I didn't go to it, but
yeah. The slides, I don't know who created them originally, but they were edited by Lady.
Yeah. No, that's just stress. So
yeah.
these are actually. Or
No, that was for EODB. Yeah, no, the database system slides, we don't have them, but I don't know if the SQ created their own for database systems as well.
I'm not pretty sure. I changed teams into.
Oh.
yeah.
Okay, cool. Okay.
Nice.
Oh yeah, so I've got there's an eraser, there's markers that I will. Oh, you have your markers! Oh my god. You should see me yesterday to that point. Yesterday trying to find markers for Harrison. Hello.
After the workshops and last minute version.
Please just monitor.
Oh, no, I'm gonna study.
All right, I'm gonna see if anyone wants to. I was lost. Okay, 15. We've got. Stop recording. No, I just was the recording button. Okay. All right, cool. So the recording has started. Ready?
I guess so.
Yeah. So I'll just stop. Screen.
What's that? Yeah, that's a good call. Let's do it.
Should be.
Okay, that is not Blackboard. That's good for me to know.
Yeah, oh, and keep in mind that if you're drawing on the board, you may need to change the camera up like that so people can see it.
Okay.
It's
Like that. Honestly, maybe just leave it like that.
Just leave it like that.
Yeah, 100%.
All right. Yes. Okay, all right. Let's get started. Hi everyone. Welcome to Database Systems Division Workshop. Before we start, I'd like to take a moment to acknowledge the traditional owners of the land on which we meet today, the Wurundjeri people of the Kulin Nation, and I'd like to pay my respects to their elders, past, present, and emerging. Just a disclaimer, this workshop is not officially endorsed by the university or the teaching staff and may not fully reflect the accessible subject content. Any tutors that participate in this workshop have verbally chosen to do so voluntarily and are not expected to represent the teaching team. Now I'd like to introduce Lucy.
Hi everyone.
CISSA.
I'm Lucy. I tutor database systems, and I'm going to take you through some of the course content that you would have covered this semester today. So this slide is more about what CISSA does. So this event is being run by DS Cubed and CISSA, both student social clubs. Highly encourage you to get involved. Evidently, you're already engaged students because you're here today. All right, cool. So we're going to cover a bit of a review on ER modeling. We're going to do a bit of a review on relational algebra, SQL, query optimization, normalization, transactions, distributed databases, NoSQL, and then general questions and answers. This subject is very content heavy, so we're not going to be able to review everything in depth today, but this is a great opportunity where if you have any questions that you're like, actually, I don't think I ever really learned how to do that. Now's your opportunity. And I would highly recommend that you ask. All right, ER modeling. Now, I can hear an echo. Can you guys hear an echo? So? Give me 1 second. Because I'm not vibing it. We need to be worried about
No,
that.
we can't hear any echo through the record, through the live stream.
I think it's okay. Online, do you hear like a problem with the sound or anything? Oh, here, is there a problem here?
I mean, it should be fine. Like I can work with it. It's fine. It's not an issue.
Okay.
I'm just worried because I know that when like you hear this in lectures and you listen to the recording later, you're like this.
I can check the live.
This is sad.
The live stream's okay.
All right, so ER modeling. Who remembers what we covered basically from weeks 1 to 3? Is this better? That's slightly better. Yeah, okay, let's do that. Cool. All right, so we would have covered constraints. So there's key constraints and participation constraints. For anyone who's wondering what the difference between a key constraint is, now participation constraint is. A key constraint is about quantity. So it's how many. It's your many-to-many, one-to-ones, one-to-manys. All right, so key, think quantity. Quantity, it's how many items you have. And then participation constraints are whether it is total participation, which means it's mandatory for all items to be involved, or whether it's partial, which means it's optional for items in your for entities in your database to have a relationship with another entity. So what that looks like is, because I feel like drawing it just makes so much more sense. Everyone can still read that, yeah? I'm going to put it there. So, this is an entity, let's call it songs. This is an entity, let's call it album. All right, and your participation constraint is going to be, so you have your relationship by default. You know that this is basically a track on an album. And then let's say that it has a many to one relationship or a one to many relationship. They're the same. Don't panic about that. All right, so this means that we have a song is going to be on one album. So the thing that is many is always going to point to the one. Now, the dumb example for anyone who's actually been in my tutes that I use is when you're in the exam and you're like, I don't know which way the arrow points. You can always think about your favorite action flick. Maybe it's Godzilla, maybe it's an alien invasion. And what I want you to picture is a crowd of people on the ground, and they're all pointing to the one Godzilla, the one alien spaceship. All right, so this is your crowd of people, and they're pointing to the one. That's how you're going to remember it, hopefully. All right, and then participation, mandatory or not. So we can say that a song can be part of an album. Maybe it's a single when it's not part of an album. That way it would be optional. If we want to depict that it's mandatory, that a song is part of an album, then we make it fig. And we also know that every album absolutely has to be made up of songs. So that's mandatory as well. All right, weak entities. So you would recall that weak entities can only be identified in relation to another entity. And weak entities are scary because sometimes it seems like something needs something else to be uniquely identified by it, or logically makes sense that it doesn't exist without it. And I think it's a balancing act in that it's possible that there will be weak entities in your assessment pieces, but you have to really justify why you think they should be dependent upon another entity in your business model. And the hard thing with a lot of business models is that most things are dependent on one another. Like if you take a university, for example, a subject isn't going to get run if it doesn't have students. Subject isn't going to get run if it doesn't have a teacher. But I wouldn't describe a subject as a weak entity, because conceptually it still exists in the handbook. It still exists outside of it. So Godspeed, it's a fragile act. All right, cool. Special attributes: multi-valued, composite, derived, and relational. Who can tell me what? Wait, does question and answer work on the recording? Sorry, if I ask questions and people answer them, is that going to work? I can just parrot what they say.
I don't think this one has that. Unfortunately.
That's fine. All me, baby. All right, so multi-valued attributes. What is the difference? No, I'm going to do it anyway. What is the difference between a multi-valued attribute and a composite attribute? Does anyone recall the really distinct difference between the two? I'll draw them up. So I need an eraser. All right, so this is a composite attribute. It has little subparts, right? And then we have a multi-valued attribute, which is actually a bonus dash. And let's call that. This is a clue. All right, so who can tell me what the difference between a composite attribute is and a multi-valued attribute? Yeah.
A multi-valued attribute can have multiple like phone numbers, for example, and a composite attribute can be like address, and it has like postcode and street address.
Yeah, so 100% correct. What we're looking at is the fact that a composite attribute, you know how many parts it's made up of. It's going to be finite, it's limited. So in this example, we have two parts, 1, 2, right? And that's it. In a multi-valued attribute, you have zero clue how many values it might have. So in the example raised by the student in the audience, you can talk about how maybe you have a list of phone numbers, maybe you have a list of favorite animals, and it could be that person might have 0 favorite animals. They might have 10 favorite animals. You truly don't know how many. So this dash, think about it as uncertainty. You're like, I have no clue how many items are going to be multi-valued. All right, derived and relational. Actually, I think I might be right. I think prices. So a derived attribute is actually this. So, sorry, just from memory, is this derived or is this multi-valued? Because I actually can't recall. That's derived. Okay, my mistake. For the record, let this show this is derived. So this would be the same as going like age if you had birthday as another entity. Because you would be able to derive the age from the birthday. And derived attributes, when you're converting them from conceptual into logical, you just get rid of them. They're implicit.
Yeah.
All right. Cool. And then let's discuss relational attributes. So if you have 2 entities, let's have that songs back and the albums back. You have track. Then you might have an attribute on this, which is number. And that might be whether it's track 1 on that album, track 12 on that album, but that attribute is specifically when you're putting a song in an album. It doesn't exist in the song, because this song, like let's say this artist re-releases this album in 20 years, and now that track is no longer track 3, it's track 20. It's specific between the relationship between the song and the album. All right, so relationships. Binary is the most common, binary being 2 entities are partaking in this relationship. Binary meaning 2. Unary meaning 1. So that's when, let's say you had students, and students can be housemates. So they would have a unary relationship with itself. It would be a housemate, because students may rent with other students. So a unary relationship is when there's only 1 entity involved in this relationship and it's to itself. And then a ternary relationship is when there's 3 entities involved in the relationship. Now, a ternary relationship, generally speaking, is going to be hard to justify. So sometimes they make a lot of sense, and sometimes they're actually better represented as, say, 2 binary relationships or something similar. So be very careful about ternary relationships in your assessment pieces. All right, notation, Chen's notation, crow's foot notation. So currently everything we've been writing on the board is Chen's notation. You'll also need to know ER. So ER is crow's foot, and you've got, let's take songs and albums. All right. So if we had this, and we know that we have the many points to the 1, then in crow's foot would be representing this as a table, songs, and then album, sorry, maybe. The relationship line, and we know that an album needs songs. In this example, we're saying it's optional for a song to be part of an album. Maybe it's a single. But in this, you would represent it that when you read crow's foot notation, what you want to do is you want to cover up 1 and you like read it. So it's like this has that. So essentially, songs doesn't have to be part of an album. So we know that it's going to be 0. And we also know that it's going to be many. So it's going to be, the many is this little like tree symbol, and the 0 means it's optional. All right. And then when you read it the other way around, albums to songs, you're looking at, we know that an album has to have at least 1 song. That's probably going to be many songs. 1 to many, because it's mandatory. All right. So just to make those symbols clearer, because I'm not very good at depicting them. So this is optional to many, and this is mandatory to many. And then if you're looking for exactly 1, that'll be that. And then if you're looking for optional 1, it'll be that. All right, so that's crow's foot notation. And when you're reading it, cover up the notation that's closest to the entity, and that's the relationship to the other entity. So you've got songs is one or many for an album. So an album has one or many songs. Songs has 0 to many albums. Actually 0 to 1 albums. Oh, wait. Okay, so album, that's the album has 1 to many songs. That makes sense. Songs can optionally be on 0 to 1 albums. Yeah. Yeah, because we specifically said that it can only be on 1 album. Yeah. All right. Chance notation, crossword notation, translating designs. So from conceptual to logical design, so you're going to need to change Chen's diagrams into ER. And then you may even have to write the physical design, which will involve you setting up some SQL and writing data definition language. All right, so hot tips. Do not include the actual business or company whose business process you are modeling. I'm sure that this was mentioned around your assessment pieces, but some students will get confused and they will try to write down the business itself. Like let's say you're modeling the University of Melbourne and then you put down university in your ER diagram. That will not help you. You want to capture students, you want to capture subjects, you want to capture staff, but you don't actually need to store the University of Melbourne as a concept. You may need to store campuses. Campuses is reasonable, but the business itself is very rarely, we don't have attributes or like we don't have things to store about it. Like what would you store about the University of Melbourne? Like the title, like you already know that this brief is for the University of Melbourne. There's nothing like tangible that you would store for that entity. All right, avoid using vague words like has to label your relationships. This one is really important. So here we didn't say that album has a song. We said the songs are tracks on albums or album has tracks that are songs. So just don't use has, like don't write it once in your exam if you're doing modeling. Don't overuse weak entities. We've already touched on that. Remember to annotate, underline for primary keys. So when you finished writing your Chens, check that every entity is a rectangle. Check that every relationship is a diamond. Check that every attribute is a circle. So composite multi-valued is a double circle. Derived is a dash circle. And then also make sure that every entity has a unique identifier. So that'll be your primary keys. So those are the ones that are underlined, right? So a song might be, honestly, it probably has a surrogate ID and SID. And that is going to be the unique way that you identify that song. Yeah. All right. And then, so surrogate IDs, who remembers what surrogate IDs essentially do? Yeah, so a surrogate ID is a made up unique identifier. So basically when you're like, I don't think this is a weak entity, but a song actually can have many, like the name can be the same between 2 songs, right? So you need something else that's going to uniquely identify it. You have the liberty to just create an ID that'll be order indexed and that'll help you uniquely identify every row in that entity. All right, proper use of relationship attributes is helpful. So again, when you're adding relationship attributes, think about, does this only occur if it's like number, track number? Sorry, the writing is very illegible. But if it's track number here, then you know that it only occurs when a song is on an album. And then we've already discussed ternary and binary relationships, and that generally speaking, ternary is only useful when a relationship must involve all 3 entities. And even then, if you read online, there's a lot of debate. All right, cool. So when you're going through an ER modeling in the exam, read the brief. Read it in its entirety, get a vibe. Go back through and then start underlining what you think could be entities and what you think could be relationships. You can also write a list, but underlining them also helps because then when you glance back up, you can see in the brief, the parts of the brief that are mentioning which different entities and relationships so that you can find attributes easier and things. Pay attention to the keywords and determining relationship constraints. So if it says must, usually it's going to be a mandatory participation. It says can, it's often going to be an optional participation. If it says a something, it's usually going to be a one or one-to-one, a one-to-many or a one-to-one relationship. Or if it says many, then it's going to be many, or like a few or whatever. Anything that's like more than one is going to be many. Even if they're like up to 6, it's still many. Because that is a constraint that would come later. In terms of modeling it, it's many. All right. And then double check special attributes. So again, those are your composite, your multi-valued, and your derived attributes. All right. Actually, there's a really easy way to remember multi-valued and derived. So multi-valued, multiple circles when you're depicting it, because you've got 2 circles, right? No more, no less. Multi-valued, multiple circles. Derived, dashed, D for D. And then composite is a compound, I guess. All right, so when you're going through your ER diagrams in your exam, list any assumptions you've made. Now, it's highly likely that the exams will be as clear as possible. So don't write a small essay of assumptions, and also don't use your assumptions to simplify the brief, because you're not going to win. They're just going to be like, those aren't fair assumptions. All right, so be really clear that you've read the brief, and only make assumptions for things that you're like, genuinely like, it could be, I truly don't know which way it's going to go, then you can write that down. Do not draw a messy final model. I think this is self-explanatory. If the people marking your exam can't tell whether you drew a wonky rectangle or a diamond, you will get marked down. Relationships, diamonds, entities, rectangles, attributes, circles. All right, now, also it's highly recommended that you check your assignment 1 feedback, because it's possible that you may have been making mistakes in your chens, and that would have been highlighted in your assignment feedback. All right, oh, and then also like really emphasize which lines are bold and which ones are thin when you're depicting mandatory or partial participation. All right, cool. So we're going to go through an exercise now. We have a brief on the board. If everyone could take a moment and essentially do what you would do in an exam. Give it a read, start writing down some keywords that you think are entities and attributes and relationships, and then we're going to go through the answer together. Yes.
Does it matter if we forget to make weak entities bold?
Does it matter if we forget to make weak entities bold? It would matter. It would absolutely matter. So when you are depicting a weak entity, you need the relationship to be bold and the entity itself to be bold. So I'll just draw it. The reason why it's critical that you make the weak entity bold is purely because this entity is being represented by, let's say, a number, and that's part of its primary key, and then a foreign key of some description. And it's in a relationship with another entity. And this has that foreign key that we talked about. And this entire relationship, so the entity itself, the relationship, it all has to be bold. And the reason it has to be bold is because you know that you cannot uniquely identify it without this other entity. So we really need to see that you understand and that you've made a deliberate choice to represent this as weak for 2 reasons. 1, we will be judging you on your choice of weak entities. And 2, we need to see that you didn't just like what's to stop a student being like, oh, maybe it's weak, maybe it's not. You're going to pick a weak entity, commit. Make it all bold. That's also the correct notation. So it's not just being pedantic, it's actually like that's how you represent it. And if you haven't represented it that way, you will lose marks. Right.
in our modeling, I didn't think it was required to put foreign keys in relations because they are implied. But in the diagram you just drew, each entity had a foreign on it. Which is the correct way to draw this, with or without?
Sorry, yes, that is correct. You will not need to draw the foreign key in your chance. That's my mistake. It is implied from the relationship. You just need to draw the fact that it had a partial key with the dash, dash, dash. So in that case, it is number. Yeah. All right, so let's go through and let's discuss which entities we reckon they are. Now, in the exam, you're going to have to do this all by yourself without anyone guiding you. So I think it's important that you try to get as far as you can. But here is the hint. These are the entities that we've identified. I'll give you all another moment to update your chens if you're already off track. Now, when we're discussing this, we actually do have one weak entity in this example. Because each artwork is stored by the maker and it's the number artwork. So let's say it's like Van Gogh's 5th work or Van Gogh's 10th work or etc. It means that the artwork can only be uniquely identified by its maker. And that is good grounds for it being a weak entity. It should be a weak entity. All right, so it's starting to shape up. Now, when you're in the exam, you'll go through and you'll be like, all right, what are the business rules? What are the relationships between these entities? So we know that customers must register a proposal for the use of the artwork. We know that each artwork may have been owned by many owners over time, but can only have one owner at a particular moment. And that is a sneaky sentence. And the Bridgman records a single maker for each artwork. So we know that each artwork has one maker. We know that each artwork essentially has one owner. Even if it's had multiple owners over its lifetime, we're only storing one at a particular moment. And customers must register for use of the artwork. And at any given time, multiple customers may have proposal permission for a particular artwork. All right, and now we've identified all the attributes. And this is the final product. So you're welcome to take a photo of this slide. I can also bring up the brief if this is something you'd like to do in your own time. And I would highly recommend it. It's just facts that the more you practice this, the better you'll be at it. Yes.
Why would proposal not be unique on customer?
Yeah. It's a fair question. Let's have a look at the terminology. So customer makes a proposal, and we know that the proposal must have a customer. But the customer may have multiple proposals. So a customer, let's have a look. Customers can be individuals, companies. We know we need to record their contact information. At any given time, multiple customers may have proposal permission for artwork. So they can have multiple. So I think, I guess the reason why we didn't consider proposal a weak entity is because it in no way in the brief does it say that a proposal is identified by customer. It absolutely must have a customer. And you're right in a sense that because it must have a customer, we know that it will always have a customer. But we can't say that it's being uniquely identified by that customer. Yeah, this is the tricky thing about weak entities is that even if something must have something and you know it doesn't exist without that thing, is it being identified by that? And it could just be something so simple as that if the customer like withdraws their proposal, whatever, or like cancels it, the proposal stays in the system. And then, yeah. All right. Relational algebra. Who remembers all of these symbols? Project, select, join, rename. All right, relational algebra. So selection, sigma, basically is going to get you the rows. So this is horizontal filtering. All right, we only want this row and this row. And then we have projection. And projection is essentially, we have rows, but each of these rows has columns. And we're basically saying we want this column, we want this column. So this is vertical filtering. And then union is similar to join. And then set difference basically means that you're looking at everything that's not neither of them. And then cross product allows us to combine two relations. And cross product will get you all possible combinations of all two tables, in that it takes one row from one table and it will match with every row in the other table. So it's pretty OP. All right. Now, the following tables are part of a database for a role-playing game. We have 3 tables: player, player, item, and item. And I would like you to write a relational algebra statement that lists the names and values of items bought by players with experience level adventurer, who are not named Colton. So when you're approaching relational algebra questions, you want to ask, what columns do we want? What rows do we want? So in this example, who can tell me the columns that we want? Yeah, so it says list the names and values of items. So we want the item name and the item value. Those are the 2 columns that we want back. So we're going to project to get those 2 columns. And now what rows do we want back? We only want the rows where the item was bought by a player with experience level adventurer who was not named Colton. So there's 2 rules there. We want a player with experience level adventurer and their name is not equal to Colton. So that's what we're selecting in terms of the rows. And in order to get both player information and item information, we need to join the tables, right? Because we can't get all that information from the one table. Good. All right. So hopefully I'll give it another minute. All right. So this is hopefully what you should have had. You want to be returning these 2 columns, item name and value. You want to be selecting where experience is equal to adventurer. And so and is always going to be a little a without the line, essentially. It's an upwards point. And name is not equal to Colton. And you want to get it by joining player with player item with item. Now, these are all natural joins, right? And the reason we can do a natural join is because the foreign keys and the primary keys in those tables are the same. So player ID is going to join with player ID, and item ID is going to join with item ID. So you can just use a natural join. Now, if your columns don't match, if your foreign keys and your primary keys don't match, you need to specify what values you're joining on. That's really important. All right. Any questions about relational algebra? I think one of the easiest things to do is like, identify exactly which columns you're wanting, identify which rows you're wanting, and then work on this like in a bit like, how do I join the tables to get both of these, like to get these conditions and to get those columns. All right. So find the names which are shared by at least one player and at least one item. Now this one is a little scarier. But you essentially want to find if someone's called Hammer. Just if the player name matches the player item. Just absurd. Yeah.
What is the syntax or notation for doing non-natural joins?
Non-natural joins.
Yeah.
Yeah. So you would essentially be, you basically would write out your table name. So it'd be, let's say, player. And then you would write essentially the ID that you would want. Player ID. And then it would be join with, and then essentially, for this example, let's say you were to join item ID from the item table. So you just essentially need to write down the key, like, sorry, the key, the primary key and the foreign key, or at least the columns that you're planning on joining up when you're specifying your join connector. And so you want the two tables and then what you're joining them on. Yeah. All right, so what are the columns that we want back? Well, we want the names, right? So we want the names only. So now that we want the item name. And then the sneaky thing is we also want the player name. And those are the only two things we want back, and they're going to return the same thing because they are equal, right? So then the next thing we want to do is we essentially want to get the item name from item, the player name from player. And then we can use a fancy little, essentially, we're going to use a set intersection. And it's going to say, get me all the columns that match this item name, where it's going to match the player name. So that one is pretty left of center. But this is exactly how it works in terms of like, this is the set intersection. So you would get only items that fit in that. So I don't know if people are drawing out the Venn diagrams, you would be able to Google them. But whenever you're doing a join, you're doing some series of a Venn diagram, right? So if it's a left join, you're getting all of this. You're getting one table, table one, table two. So in a left join, you're getting all of table one and any of the rows that are in table two. If you're doing set intersection, you're going to get this bit. So this is what we've done here. We're only getting the bits where they match. Yep. And then if you're doing a natural join, you'll also probably get this, but it's just that you don't have to specify the columns that they're on. Yeah.
Is joining players straight to item the same as natural joining player item, and the natural joining that item?
Once more, please.
Is joining player straight to item the same as natural joining player to player item, and then natural joining that to item? So player, natural join, player item, natural join that.
Those two things are not equivalent. If you're saying join player to player item, then that's all you're saying.
And then after that, natural join that with item.
Okay. If you natural join player item and item, that will work because they have this cascading relationship of like primary key, foreign key, primary key. So you're going to be able to match all of those up. If you are directly joined, say player, the table player with the table item, you cannot use a natural join because there's no two columns that share the same name, right? Player ID? None. Player name? None. Experience? None. So you're going to need to specify the column that you're joining on, right? And in doing so, it's just not the same as doing like a natural join between the three of them because you're actually going to get kind of wonk data in that, like you're essentially saying like, let's join the player ID on the item name. But those two things represent different attributes, like different quantities. So when you're joining them, you're making the data a little less, like it's more confusing. So you have to be really smart about the way that you're joining things. Yeah. Yeah.
Join player and item on player name equals item name and then projected the name. Is that a valid solution or is that too complicated?
No, I think that would be a valid solution. Because you're essentially only going to get the rows where, like, if you're joining, so whatever you're joining on is in both tables. So if you're joining on the name, sayonara. So if you're joining on the name, then the reason why this works is because this value, when you set intersection with this value is the same as this value. Like the whole thing we're finding is that these two names are matching. Now you can also write this out as select the column name, and that can be either player name or item name, because they're going to end up as the same value. Like that's specifically what we're looking at. So you can also do like project either player name or item name, up to you, personal preference, it's not going to matter. And then you can basically be like join player and player ID with essentially, sorry, not player ID. We cannot join using player ID. Player name, join item name from item. That would also be valid too. Okay. SQL, everyone's favorite. All right, SQL questions. So it's very likely there will be SQL related exam questions. Sometimes they base it after the assignment 2. So I would highly recommend everyone review assignment 2. It's very unlikely that they will be asking you questions that are the difficulty of, question 9 and 10, but they might be asking you up to a question that's maybe question 7 difficulty. So revise assignment 2. It also helps you just revise like how to write SQL statements. And you can also try and make up your own questions as well. All right, so keywords. Select. So select is going to get you back your columns. It's very similar to project. Distinct will remove duplicates. And you can also use aggregate functions. So you can select the count, you can select the sum, you can select the average, min, and max. Okay, from table A. So from, that's where you're getting the data from. Which tables are involved in this SQL statement? Where and or. So where are your conditions? That's essentially your little sigma symbol. And it's ensuring that the rows satisfy the conditions. Then you can group by. So if you have an aggregate function like count, sum, average, min, or max, you can also group by. And group by would, if you were to group forum.id, it would group rows so that all rows with the same forum ID get combined in some way to one row. And this is useful when you're using aggregate functions, as mentioned. So your counts, mins, maxes, sums. Having is essentially your where condition, but specifically for aggregate functions when you've done group by. And then order, that's, I'm hoping, fairly self-explanatory. Order is the order in which those results will be returned. It can be by a specific column value, and it can be ascending or descending. So it might be like name, alphabetically ascending or alphabetically descending. And then the limit just essentially adds a hard limit on how many rows it will return. All right, types of joins: natural join, inner join, outer join. So natural join is when the two column names match. The MySQL statement is going to know implicitly which columns you want to match because there's only one column that matches in those two tables. Now, if there is, for example, multiple columns that match in terms of column name, you may need to specify exactly which columns you want. Natural joins really only work when you have a uniquely named primary key and foreign key. So in the previous example, we had player ID, and then we had a foreign key player ID in the other table. Because they're both named the same, you can just join them up. But if you were to have, let's say the player table just had ID as the column name, and then your player item table had player ID, you actually need to specify that you want player.id joined with player item dot player ID, essentially. When in doubt, write it out. Just be really concrete about like what you're joining on. All right, so inner joins specify the condition the table is being joined on. So table A, inner join table B on, and these, then you would specify the two columns that you want to join on. So table A.id equals table B.id. Outer joins, so this will include records that don't have a match. So outer joins, when we were talking about this Venn diagram as before, we were saying that natural joins end up here, set difference end up here, like a lot of the natural joins are going to end up here. So natural join can be written natural join, or it can be just written join. This is quicker. Use this. Time is of the essence. But if you're doing an inner join is also going to return the same part, but this one you have to specify which columns. Yeah. Cool. And then the other thing that we have is outer joins, which is if you're doing a left join, you're getting all of this. And what this means that it's returning this table in its entirety. And where it can match with the table 2, it will. But it's still going to return the entire table. And it's the same but opposite for right outer join. So if you have a right outer join, left outer join. Left outer join. And it's the same for a right outer join. So a right outer join will get this table. Right. Outer join. Now, what you're wondering is, well, which is the left table and which is the right table? Depends how you write the statement. So if you're saying join, like join table 1, table 1, join table 2, sorry. Whoop. Anyway. Table 1, right join table 2. Then table 2 is the right join. And in this case, this is still written table 1, join, well, okay, left join. Left. Two, and then that'll get you this one. And the thing is if you swap the order of these tables, let's say you had table 2, left out join table 1, you end up getting just the right join. And if you have table 2, right join table 1, you end up getting the left join. So your left table is always the table that you've specified first in the join. And a full outer join means that you get everything from both. Yeah.
When do we use the distinct keyword?
Yeah, so
when would an outer join be more useful than an natural join?
okay, so an outer join essentially means that you're going to get all the information back from both tables. So if your question says something like, what is a good example? We want all owners and all pets. And we want to know which owners own which pets. Essentially, like, and the reason I'm saying that is just that you end up returning both tables in their entirety when you do an outer join. You also can see where they've been joined, but let's say that some pets are in the shelter and they don't have an owner, you're still going to get all of those pets. And let's say you're doing the shelter and you have, instead of owners, let's call them adoptees. So you have some active adoptees that already have pets, and then you have some adoptees that may not have pets yet. So you can do a query that's going to return all of those rows. You're still going to see which adoptees have pets, because that's going to be part of your join. But you also will include rows from adoptees where they don't have pets and rows from pets where they don't have adoptees. You're just going to return everything from both tables with a full outer join. In terms of left outer join and right outer join, that means you're only getting one table back in its entirety. So there may be questions which is like return all administrators, including those that have one something or other. So if it's including and you've been asked to return all values from one table, then you know that you're returning all values from one table, regardless of whether or not they have, whether or not they participate in this join. Yeah. And then what's the second question?
When do we use the distinct keyword?
Yeah, so distinct keyword gets you back only one value. So one example might be, let's say you're trying to find all the employees by department. What you're actually going to end up with is, let's say you have 4 employees in one department. That means that department is going to turn up 4 times in your results. So when you use distinct, it's basically only going to get you the department once because it's the distinct value for that department. Yeah.
Another question. So are inner joins functionally the same as natural joins? The only difference being that you need to specify the joining columns for inner joins, whereas this is done implicitly in natural joins.
Correct. Yeah. So in case the recording didn't hear that, natural join, join, and inner join are functionally equivalent. It's just that inner join, you need to specify the columns you're joining on. And that's usually used when the column names don't match, when you're doing something a little bit odd, like not joining primary keys to foreign keys or something. Great. Subset queries and set operations. All right. So subqueries are going to be important because it's highly likely you will get a couple of complex SQL questions. Don't be afraid to use a subquery. And also, I know that in the assessment pieces we talk about a lot about making it as simple as possible. And there is highly likely to be simple answers for some of the questions, but there also will be questions that might genuinely just be complex. And it's better that you write something than get panicky about it being the most simple solution. All right, so subqueries, in or not in. So you can have like select from where. So you can write out a subquery and then check if it is in or is not in that subquery. You can also check if any of the rows are true or true if any of the return values meets that condition. You can do if all of the rows return meets that condition, and you can do exists. So you can just say like if one or more rows exists. All right, and then set operations, which are also supported by MySQL. You've also got union and union all. So union is the same essentially as a full outer join. Cool. All right, unary joins and aliases. So if you are doing a unary join, because we know in Chen's that there are unary relationships, if you're doing a unary join, you need to use an alias. So in this example, we have, this is from week tutorial 5, so this is week 5. So select emp. We've done a little alias here. We've said we're going to call this employee table as emp. We're going to call one instance of it emp. We're going to call a second instance of the exact same table as boss. And the reason we're doing that is because we want to know which employee has which boss, essentially. Now, specifically, this is to work out which employee, like which boss is making like more than twice the salary. So yeah, employees whose salary is less than half that of their managers. So we need to know the employees, what their salary is, and then the boss, what their salary is. And we need to be able to keep those two concepts separate. And in order to do that, we need to use aliases. So we've got the employee and what their salary is going to be eventually. Then we've got the employee as the boss and what their salary is going to be eventually. So now we have these two separate concepts, and that's going to help us answer this question. So then we have inner join, then we've done this inner join. And because both the boss has an employee ID and the employee has an employee ID, but we specifically want to know for those employees that have a boss, how much does their boss make? So then we basically are specific. We're saying we've got this concept of the employee. We want to know what their boss's ID is. And then we say, if that employee's boss's ID, which is the boss's employee ID, then we know that this employee has that employee as a boss. I know it's confusing. Unary relationships, this is worth digging into. It's really cool. Aliases are very cool. And then we can basically say where the employee's salary is less than half. So we've taken the boss's salary, divided it by 2, and we're saying that the employee's salary is less than half what the boss's salary is. Okay, so golf case study. We're just going to give this a quick squiz. There's going to be some questions, SQL questions related to this, and we have a database schema on the next slide. So this brief isn't critical, but have a quick read because it'll give you some context. All right, this is what the database schema looks like for this golf club tournament database. So you've got courses, you've got holes, you've got players per hole, you've got player competes, you've got players, and you've got tournaments. Now, I would like you to write an SQL query that returns the names of the tournaments played at courses in the suburb of Heatherton, where Bella Sandbury, a player, ranked in the top 10. This is going to take you a little while. So work out what you want to get back, work out what the conditions are, and then try and knit it all together in one giant SQL statement. right, so what do we want to get back? What is the column that we want back? Bingo. Now, is there a chance that this could return multiple values of the same tournament name? Yes, so we're going to write distinct. And name from. Now, which tables do we need to answer this question? So we have a few conditions. Spoilers, we have a few conditions. We need to know that the course was played in the suburb of Heatherton. We need to know the player's name. And we need to know the player's rank. Right? And we also, so we definitely know that we need the tournament table because we're returning the tournament name. What other tables do we need? Yeah. And if we're getting player, what's an easy way to make sure that this player has participated in this tournament? Yeah. Yeah, so we're going to join tournament. Oh, sorry, this is join player complete. And then join player. And then we also need to get the course, right? So luckily we can also join course because each tournament has a foreign ID for course. Join course. Great. Now, what are the conditions? Where? What's the first condition in that statement? Played at courses in the suburb of Heatherton. What do you reckon? The course suburb needs to be equal to Heatherton. All right, and what else?
Their first name, that one, second name, the house name.
There you go. Yeah. So player. So we've got dot first name to Bella. We also need to know that their last name is the same because there could be two Bellas. And three. What else? There's one last condition. Say that once more. Bingo. Yeah. So when we look at the player competes table, we've got rank. So we can go rank is less than or equal to 10. Yeah.
Two questions.
Yeah.
When actually that's not the short one. Can you refer to player dot first name? That's just the first name.
Yes, you can, because in these, sorry, let me take it back a slide. In these tables, none of these other tables have a column called first name or last name. So when you join these four tables, there's only one column called first name or last name. So you don't actually need to write player dot. You can just write first name, last name. Because the database is going to know which column you're talking about in that 4-column table. Yeah, next question.
The other one is when these queries on paper, how important is it that we get correct syntax regarding curly braces or naming with a subquery?
Subqueries usually happen in regular brackets, not curly brackets. Crazy.
That's the only one.
Okay, so we'll look.
Yes.
Yeah. Yeah, syntax is pretty important in terms of like if you're writing this code into a database and you get the syntax wrong, the query won't run. Now, I do believe that the teaching team are going to try and give you as many marks as we can within reason. So please do be conscious about, I guess, like adding a semicolon at the end. It's not hard. You can do it. I believe in you. Wrapping things in little brackets, like those brackets help us know exactly what your subquery is, what that is going to return, and then how you're using that in your larger query. So yes, syntax is going to be important. Yeah.
Put the same result underneath the balance.
Yeah.
Be achieved if you did post suburb equals Heatherton.
Yeah.
And Bella Sandberg in and then subquery. Select first name from player, join player to goods, where rank is less than or equal to 10.
Yeah. Yeah, you could easily do a query that had these two and a query that had essentially probably like, yeah, these two, because the tournament ID, you'll be able to match those up in your subquery. So it's possible. Yeah, it's possible. 100%. All right, query optimization. Cool. So everyone remembers this mass of formulas that they're expected to know? Yeah, cool, good. So basically the tips for formula for query optimization is understand the formulas in the cheat sheet. It's actually really important. It will help you in the exam because you'll actually be able to remember things quicker, and you'll also understand how it works when you are pipelining between consecutive joins. So you also may be asked questions such as like, what does the 2 in 2 times number of passes, number of pages means when you're discussing a sort merge join? For those of you who don't know yet, the 2 in a sort merge join is essentially that one is the cost of reading it in from memory and one is reading it out from memory. Because when you do a sort merge join, you're going to have to read in all the tables from that database, sort it, save it, and then you do that again with the other table, read it in, sort it, save it. And then when you join them together, you just read them essentially. And because they're already sorted, they're basically just like reading it like read. All right, what is the B in block-orientated nested loop join? B is for buffer size. So your blocks are only as big as your buffer is. And so you'll need to be able to calculate that. What is the 3 in a hash join formula? So 3 is basically that you're reading it, you're writing it, and then you're reading it once more. So it's similar. Well, I shouldn't say that, that'll confuse you. But yeah, essentially you're reading it in, you read that database in, you hash it, you save the hash version, you read the other database in, you hash it, you save that, and then you read it back in once more, and again you read it, and it kind of like reads them together. And because they're already in buckets, they've already been hashed, you can just like add those buckets together. And so on. All right, so yeah, you may be asked either multiple choice questions or short answer questions potentially on that, so it is worth knowing. All right. Be careful about the usability of indexes, right? So who remembers talking about how indexes can have composite search keys? Yeah, so composite search key on an index basically means that it has, let's say, the example used in Tutes is often age and salary. Now, if you have an index that's indexed on age and salary, you can look up queries that are asking for the age. You can look up queries that are asking for the age and salary. You cannot necessarily look up queries that are asking for is dog owner. That's a Boolean. That's not going to work. You have to think about the order in which you get your composite keys. Because not all indexes are going to be applicable. And it's also that just because an index exists doesn't mean it's on the column that you need it to be. So if you have an index on age and somebody wants to know the date that they joined the company, that index is useless to you. All right, so hash index. Hash indexes cannot do range queries. A cluster index can do both equalities and ranges. Sorry. A B+3 index can do both equalities and ranges. A clustered index means that the index that you've saved on that value, let's say you've got an index on age, all your files saved on the computer, they're sorted by age. So it means that when you're matching them up, the arrows won't cross. So hopefully you would have seen in your lectures and in your tutes a diagram of a clustered B tree versus an unclustered B tree. And you would have seen that when it's clustered, none of the arrows pointing from the leaves in your B+ tree to your files in your computer, none of them cross because it's in order. But when you have an unclustered B+ tree, there's a bunch of crisscrossing, and it's because it's not sorted underneath the hood in the same way that your index is sorted. All right, reduction factor. So reduction factors decide the cost and result size. It's an approximation. So the result size essentially is the projection. Well, it's the product of all the tuples in one table by the reduction factor, the product of the reduction factors. I would highly recommend you write out your own formula sheet so that you can understand what's going on. And when you get to a symbol that you're like, well, Google it. Look it up in your notes. Look at the lectures. Yeah.
When using pipelining.
Yeah.
One of the costs is ignored when calculating cost.
Yeah.
In the hash join algorithm.
Yeah.
Which n pages is ignored? One of the 2 n pages or the n pages?
One of the
2 n pages or the n pages?
hash join. So hash join is essentially, you can either write it out as 3 bracket number of pages in S. I think it's number of pages in let me double check that one. Or you can write it out as 3 times by n pages of S plus 3 times by n pages of R. And what this essentially means is that these two are equivalent when you're doing your hash join. And when you're pipelining, I would separate this because you can only drop one side and you would drop the one that you're not reading in. So usually that means the outer table. So writing hash join like this might feel succinct and good, but you have really high potential to muck up a pipelining join. If you write out your hash joins as 3 plus 3 times, like 3 times the number of pages plus 3 times the number of pages, it's much more intuitive to drop one of those read-ins because you can't drop this to 2. You will not get the correct result. You can drop one of these 2 to 2. Does that answer the question? Okay.
I think so. I'll check if they have any follow-up.
Okay, beauty. All right, cost depends on the search key fields in the index and the query predicates, and you should only consider the matched attributes. Result size depends on the query predicates. So your result size is essentially just saying that you're only going to get back rows that match, and it's going to be smaller than the total size of the database. All right, so consider the relation, that there is a table A, a table B, and a table C with the following quantities. Now, using this join flow, what is the total cost of doing those 2 joins? The nested loop join, page-based, and the sort merge join. All right, I'm going to give you 5 to 10 minutes. Probably more like 10 because it's complicated.
with pipelining and SMJ.
Sort merge join, yep.
Oh, yeah. Oh, okay. Which read is ignored, and read cost is ignored.
Yeah, essentially because sort merge join is balanced in that the formula for sort merge join is that you have 2 for the read in, read out times the number of pages in one table times by the number of passes. Plus 2 times by the number of pages in the other table times by the number of passes. And then you essentially go plus, you read in both, like all the pages from one table and all the pages from the other table to join them. So this is specifically the sorting part of the sort merge join, and this is specifically the merging part of the sort merge join. So when you're pipelining, essentially you will not need to, so this is read in, read out, and this is you sorting the pages. So if you don't need to read it in, you can essentially just drop one of these. But you'll still need to read in the other table, sort it, and save it.
So is the read cost in the sort that is ignored? Is it the read cost in the sort that is ignored?
Yeah, so pretty much in every example of pipelining, you're ignoring a read because you have the result of a previous join already in working memory. So you don't need to then go fetch it from the hard drive because you've already got it. Yeah. Really don't. All right, for the sake of time, we're going to launch into it. So first thing you do when you get a question like this is write out everything you know. You write out every single table you have, and you write out how many tuples each table has, how many tuples per page that table has, and how many pages therefore it has. I want you to be so concrete with all the information that you have. You write out if there's any indexes on a given table, and then you also write out how many pages per join there are. So if you were to join A with B, or B with C, or for that matter, C with A, you would all get 10 tuples per page. And that's really critical. And we know that because it says 10 tuples can be stored per page for all joint results. And we also know that 2 passes are required to sort. So that's also worth writing down, 2 passes. Okay, so then we start with the page-based nested loop join. Who knows what the formula for a page-based nested loop join is? All right, so with a nested loop join, every time you think about a nested loop join, you think about 2 for loops. Okay, one is the outer for loop, and if it's tuple-based, it will be tuples by pages. If it's page-based, it'll be pages by pages. And if it's block-based, it will be blocks by pages. So what that means is that when you've got a page-based nested loop join, you're going to end up with the number of pages in R. You're going to read them in, and then you're going to do the number of pages in R by the number of pages in S. So this is your for loop. So you're saying that for every item in your outer loop, you're joining it essentially with every item in your inner loop. All right, so that means that you're going to end up with, for this nested loop join with B and C, you're going to end up with, so let's say our outer table, generally, when you're doing this maths, it should be the smaller one because you're adding it on. So the smaller of the 2 between B and C is, you've got 6 pages in B, 100 pages in C. So we're going to pick B. So you've got 6 plus bracket 6 times by 100. All right, and that's gonna get you 606. Right, so you've got 606 read in and outs, input outputs. Yep. So that's the cost of that. But we also need to know the size of that because we're joining the result. Yeah. So for every join, essentially, the theory states that there's an equivalent left join. And what we mean by that is that for efficiency, they don't really mind whether you do B or C, C or B. Like you can swap that. The join still ends up the same. As we're saying, there's an equivalent left join. So you can have B on the left, you can have C on the left. They're going to end up equivalent by the time you get here. So to make your results the smallest they can be in terms of cost, like if we're talking about the cost of a query and the efficiency of a query, it makes sense that you would always want to pick for nested loop joins, the smaller table to be the plus, because then you end up with the smallest cost. Like if we reverse this and we did like 100 plus 6 times 100, you get up to like 700 IOs, and it's just more expensive. All right. And then, so we found the cost of that. Now we need to know the resulting size. So the result size formula is essentially going to be when you're doing a join. Yeah.
Yeah. You're given a question and that diagram, but C and B switch.
Yeah.
Would we do it, and C is the outer one, even though it's more efficient, and calculate it that way, or would we calculate the more efficient version?
Yeah, I'm not sure what the marking metric on that is. So I actually would possibly ask Ed. I just don't have the capacity to give you a definitive answer on that. And I would hate for that to affect your grade. My understanding, and this is mine alone, is that essentially like wherever you can choose the more efficient join, do so. Yeah. Was there another question? Oh, cool. All right. So the result size is essentially for a join, you're looking at the number of tuples, the product of the number of tuples in R, and then I'm pretty sure it's times by the number of tuples in, yeah. So the product is going to be, the product of the number of tuples. It's going to be in both tables. And then it's all by the reduction factor. Or the name of your color. And what that means is that we end up getting all the tuples from B and all the tuples from C. So we're looking at 300 times by C, 100. And we're going to times it by the product of the reduction factor. Now, when you're doing the product of the reduction factor for a join, you're just looking at the reduction factor on the join value. So in this table, we know that when we're joining B and C, the foreign key between B and C that's shared is going to be BID. So we're looking at the join factor. BID we know is the primary key of B. And since it is a primary key, we know that there are 300 values for it. Because there's 300 tuples, and if it's uniquely identifying B, there can only be 300 values for it. So then we do the reduction factor. So we've got an equality because it's in a join. So equality is essentially 1 over the total number of values, right? Which we know in this case is 300. All right, so then we come in here and we go 1 over 300. 100 is supposed to be 2000. Oh yeah, sorry, thank you so much for that. You are correct. That is just a little brain fog. For the number of tuples in C and the number of tuples in B. Correct. Yeah. Cool. And then we're doing it by the reduction factor. So then these numbers are going to cancel out, and you just end up with a result size of 2000 tuples. Now, what is very critical? There is something super critical about this step. Yes. All right. So whenever we're doing joins, we're going to do them in pages. All right. So we need to know how many pages this is. Now, what do we read in this line here? Yeah, for every resulting join, and this is a resulting join, there's 10 tuples per page. So this means that we end up with 200 pages for the join of B, join C. All right, that's the result size. So my hot tip is also add units to everything that you write. because when you're doing result sizes versus IO costs versus anything else you're going to be calculating, you probably will get confused. So always write down unit. Okay. In the sake of time, I'm actually going to skim over this because we've got so much content to cover. Yeah.
How do you calculate the reduction factor for joining between two tables? Is it normally one over min couples between A or B?
Yeah. So basically when you're joining, the reduction factor for a join is it's said as essentially the product of the tuples, which is the tuples times the tuples, and then the product of the reduction factors. But it's misleading because the product of reduction factor when you're doing a join is essentially you're just looking at the column that you're joining on and you're calculating the reduction factor for only that column because that's determining your result size because you're only going to get results that match that value in the two tables. So the only times where essentially, because you see how like when we did it here, kind of like cancelled out, which was really cool and we loved it, it was so good. The only times where that's essentially like not going to happen is usually when you have a composite primary key. So I think there's an example in the tubes where we do a composite primary key. I would recommend that you review that. That's probably as hard as that's going to get. Otherwise, it's essentially just going to end up being similar to what we did where we look at if it's a primary key, then we know that that primary key is like uniquely identifying each row. Therefore, we know that there's 300 values because there's 300 tuples and it has to be uniquely identifying. So then we can use the reduction factor of quality because it's essentially like where this equals that. All right, cool. So this is us calculating the number of keys, number of tuples and C's. So that is our result size. And then we're going to get the cost of the nested loop join, which is page based. So we've got the number of pages. Sorry, this one here, number of pages plus number of pages times the number of pages. And that ends up with 606 IOs. And then we're going to get the cost of accessing A, which will require you using an index scan for cluster B plus 3 index. Yeah. 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 Okay. So this reduction factor is because of the join, right? So let's go back a page. All right. So this reduction factor, we're saying we're getting the result size of this join. Yeah. So we know that this reduction factor is because of the join. And when we have a join, we have one column in one table is equal to another column in another table. Yeah. So when we're looking at these two tables here, which columns are we going to join? Like which column in these two tables B and C are we going to join on? Let's say it's a natural join. Yeah, no, that's fine. So if we're doing a natural join, we know that the column name in one table has to match the column name in the other table. So if we take B and C and we join B and C, what is the only column those two tables can naturally join on? Okay, does B have a CID? Does table B have a CID?
No.
Does table C have a BID? Yes. So which column can we join table C and table B on? Yeah, it's going to have to be BID because BID is the only column that's shared between those two tables. And because we know that it's the BID that we're joining on, then we know that we're only looking for the values that are going to match between those two. And we know that there's 300 unique BIDs because there's 300 tuples. So we know there's 300 values for BID. So we're only going to get like a maximum of 300 joins. Does that make more sense around why we used BID in that instance to?
English says a maximum of.
Yeah, it's misleading. No, honestly, it's misleading. That's why I really recommend that you write out the formulas yourselves. And it is the maximum in that, like if you have a composite key, like it becomes. Yeah. So yeah, there's probably an example that does live up to that particular rule. But for the most part, you're just looking at the column that you're joining in. Yeah. All right, cool. Where were we? Cool. Cost of accessing A. So we get the cost of accessing the cluster B plus tree on the index. Then we get the cost of sorting B plus C. And now note that we essentially, we didn't drop it. Why didn't we drop it? Interesting. Oh, that's the formula. Okay. All right, we will revisit this. We have more content to cover. Normalization. All right, who remembers normalization? Yeah.
We find the A bar, especially because we're using an index scan, and that's a B plus tree on cluster B plus tree. So it's basically sorted, so that's why we don't sort it, right?
Yes, that would be correct. So this cost here is essentially the sorting of B join C, which is this join here, and we need to sort that because we need to sort it the same as the index scan, and the index scan will be sorted assuming that you're joining. Oh, actually, you know this for a fact, because if you look back here, sorry, these two tables, right? The only attribute that you can join table A and table B on is AID, because it's shared between the two tables. And you know that the index is getting you AID, because the index is on AID. So by the time you've read in the index, you'll have all the AIDs sorted. So you don't need to sort A, that is correct. And then all you really need to do is sort the nested loop join to ensure that it's also in the same order as your index and sort it on AID. All right. And then you add the cost of your first join with the cost of your second join to get your total IOs. That's also really important. Always add it together at the end. All right, normalization. All right, so why do we normalize relations? Okay, most of the databases you deal in this subject will be normalized. The only reason why we denormalize data is to make it usually more efficient or more performant. But usually it means that it's coming at the cost of data integrity and data consistency. All right, so there's 3 anomalies that come with denormalized data: insertion, deletion, and update. Now, insertion is when you cannot insert certain attributes without having to also insert other attributes. We'll see an example soon. And then deletion anomaly is the accidental loss of attributes due to the deletion of other attributes. So if you had a denormalized Excel spreadsheet or database that you wanted to store both patients and doctors, and all that information was in one row because it's denormalized, then you might say want to delete a doctor and you might lose patient data because you had to delete all the rows that doctor was involved in, and that gets rid of the patient data. When you go to insert a new patient or add a new doctor, then you're going to have to end up adding information for whichever one you didn't want to add. And then when you have an update anomaly, it's similar in that, like, let's say you update one row and a doctor's address has now changed. Let's say they've changed their address, they've moved. You now have to update every single row. And if you only update one, then you have an update anomaly, because in an ideal world, you update the doctor's address once, and that's seen by the whole system. And that's what you get when the data is normalized. It's not what you get when it's denormalized. So normalization is the process of taking larger denormalized tables and breaking them into smaller tables. We have 3 normal forms. First normal form, remove repeating groups. Second normal form, remove partial dependencies. And third normal form, remove transitive dependencies. All right, so first normal form is basically look at the cells. Do they have multiple values inside of them? Most of you would be aware that in relational databases, we don't have lists. So if you start seeing lists, that's a hint that it's not in first normal form. All right, remove repeating groups of attributes. Okay, so essentially you just want to take those repeating groups and break them out into their own table so that you can, essentially what you would similarly do with a multi-valued attribute when converting from conceptual to physical or logical. To achieve second normal form, who can tell me? So we want to remove partial dependencies. Can anyone recall what a partial dependency is? Yeah.
Attribute that depends on.
Yeah, almost. Pretty much bang on. So a partial dependency is an attribute or set of attributes that are dependent upon
part of the primary key. So in the table we were just talking about, when you have doctors and patients, your primary key for those rows might be the doctor's ID and the patient's ID. And you have partial functional dependencies because all that patient data is dependent upon the patient ID. And all of that doctor data is dependent upon the doctor's ID. So you have partial functional dependencies. And it makes sense to us that we would split those apart. And that's precisely what a partial functional dependency, that's what we're getting rid of. And then the last one is a transitive dependency. Who recalls what a transitive dependency is? Transitive dependencies are my personal fave, to be honest. Transitive dependencies just mean a non-key attribute determines another non-key attribute. I like them. They seem relatively simple. All right, normalized to third normal form. So we have this this table, meals ordered. It has an order ID and a dish ID that's making a composite primary key. And we have the following functional dependencies. Please spend a few minutes trying to break this table down into normal form. All right, we're going to zip through this fairly quickly. Is this table in first normal form? Yes, it is actually, because we can't see any lists, which means we can safely assume that every one of these columns has one value. So it's in first normal form. Is it in second normal form? No, it's not. Why not? We have some partial functional dependencies. So we can see that we have a composite primary key, order ID and dish ID, right? 2 underlines means we've got a composite primary key. And we can see that order ID is determining customer ID and customer name. And that dish ID is determining dish name and dish price. So this means that we have these two are partial functional dependencies. So we need to resolve one of them. So we essentially would move out dish ID, dish name, and dish price. And whenever we break data in our original table into a smaller table, you take the information that's dependent on it and the information and the functional dependency. You take these 3 values, you put them in a new table, right? But what's also really important is that you leave the dish ID in the original table because you still need that information to refer to your new table. All right, and then lastly, we have a transitive functional dependency. Can anyone identify what that is to get to third normal form? We're looking for a non-key attribute determining another non-key attribute. Yeah. Bingo. So this customer ID, he's not a key, right? And he's determining another non-key attribute. So that's our transitive dependency. So the last thing we want to do is we want to break out customer ID and customer name to their own table. We keep customer ID in the original table as well. And so then we have essentially meals ordered becomes we've got the original table, which is the ordered dish. So that's the order key and the dish ID. So that composite primary key that we had originally. Then we have the order itself, which is the order ID and the customer ID. Then we have the dish, which is the dish ID, dish name, and dish price. So that was one of the first things we did to get to second normal form, because that was the partial functional dependency. And then we have the customer, which was our transitive, because we knew that customer ID determined customer name. Cool. All right, transactions. So transactions, DB transactions, and ACID. So ACID stands for atomic, consistent, isolated, and durable. So it's really, I find this one of the harder concepts to wrap your head around, because pretty much everything you do in a database these days is based on transactions. So it's actually really hard to think about how dysfunctional it is when you don't have transactions. But we basically want certain guarantees around the state of the database before, after, and while performing a series of SQL CRUD operations. So CRUD just stands for creation, retrieval, update, and delete. It's not critical, but it's an acronym that's used broadly. So creation, retrieval, update, delete. It's very similar to your anomalies. All right. Yeah. Yeah, no worries. So yeah, atomic, isolated, durable. So essentially there's 3 different types of problems. There's the lost update problem, the inconsistent retrieval problem, and the one other one. And I think anyone who wants to chat about this, you're more than welcome to chat to me after class, after workshop. And this is an example of an inconsistent retrieval problem, which usually happens when you're aggregating data. So in this example, we're getting the aggregate, we're getting a sum, so we're aggregating data. And it means that half of these aggregation values have the new values, half of them don't, approximately. Some of them do, some of them don't. So you get inconsistent data. That's why it's called the inconsistent data retrieval problem. Now, the question is, which ACID property is primarily responsible for preventing this problem? I know that's a scary question. It takes a bit of lateral thinking. Yeah. Bingo. Bang on. So isolated. So because these 2 queries, Alice's query and Bob's query, were not isolated, they weren't in the ACID principle, they weren't done as a transaction, Alice was seeing some of Bob's updates, but not all of them. So Bob's updates weren't isolated. Bang on. So isolation guarantees the concurrent execution of transactions and leaves the database in the same state as if the transactions were executed sequentially. All right, distributed DBs, they're good at scalability, they're efficient, they're fast, and they're like globally available. The con is they're more complex and you have cap trade-offs. So no SQL database can have all 3, which is consistency, availability, and partition tolerance. You always need to pick 2. And there's also types of distributed DBs. There's centralized, partitioned, and replicated. I would take a photo of this question and I would do it in your own time because you might learn something, who knows?
And I checked the slides.
Fantastic.
I'll also try to get them please.
Beauty. And then, yeah, that's the answer if you guys, well, I got the slides, so I don't need it. And then NoSQL, pros and cons. Thank you all so much for coming today. There is a lot of content to cover in this course. My biggest tip for your exam is move fast. If you're strategic, you can even look at how much each question is worth and make sure that you don't neglect large weighted questions. Like if you have a question that's worth 12 points in the end and you don't get to it, devastated. So move fast and be strategic if you can. Thank you.
Big thanks to Lucy.
No, they already clapped. Okay, I got my face.
All right, cool. What is the recording? Yeah, you're getting past. Thank you. All right, I'll end the meeting. Oh my God, hello.